We wrap up this week by showing how the results we've covered give even more geometric information about a measure whose densities exist almost everywhere. So in the last 2 weeks, as we covered tangent measures, we've slowly uncovered more and more information about the tangent structure of measures whose densities exist almost everywhere. So last week, for example, we proved Marstrand's theorem that said that if the m-dimensional densities exist almost everywhere, then m must be an integer. And in that case, the tangent measures are always uniform measures. Now, recall that uniform measures aren't necessarily flat. They could be conical. But this week, when we discussed the tangent measures of tangent measures or tangent measures theorem, we used that result to show that a measure whose densities exist almost everywhere must have at least one flat tangent measure at almost every point. So hence, so far, we know that if densities exist almost everywhere, all tangent measures are uniform, all tangent measures are uniform, and at least one must be flat. It turns out that if this is the case, then that forces all tangent measures to be flat. So in particular, we have the following result of price, that if a Radon measure mu has m-dimensional densities existing almost everywhere, then all tangent measures of mu are flat measures. And in fact, more is true. So in Price's original theorem, he actually states that not only are the tangent measures flat almost everywhere, but at almost every point there is only one tangent measure up to a constant multiple. So to discuss that result, we'll need to first introduce the notion of rectifiability, which we'll do this next week, and then that will complete the proof of Price's theorem. In fact, Price's theorem originally just states that a measure whose densities exist almost everywhere is a rectifiable measure, but we have yet to define what that means. So, but in order to prove that result, we need the technology that we built in the last couple of weeks, and in particular, this theorem right here. Now, in fact, the material from the last 2 weeks all comes from Price's original paper. So there he introduces tangent measures, cones, the TM theorem, and he even gives the proof of Marstrand's theorem that we covered last week, which of course wasn't Marstrand's original proof since tangent measures didn't exist at the time. However, one part of Price's theorem that we will not cover is the following lemma. So in a nutshell, this says that if we have a uniform measure mu, which is approximately flat in the sense that for all balls of radius r at least 1, our measure mu inside those balls is at most d sub r distance epsilon away from the cone of flat measures. So if you have a measure satisfying this condition, then that measure must itself be a flat measure. So you can think of this as a sort of Liouville's theorem for uniform measures. So recall Liouville's theorem said that all bounded analytic functions are constant. So here we have all approximately uniform measures. All approximately flat uniform measures are just flat. Another way of thinking about this is that in the space of uniform measures, the flat measures form sort of connected component of the space of uniform measures. And there's this gap in between flat measures and the non-flat measures. Now, the reason we're going to skip this proof is that it's basically 40 pages of estimating Taylor series coefficients. And while the part of Price's papers we've covered so far will be useful for us in the coming weeks, these Taylor estimates won't be. So we'll just take this result as a black box and sketch the remainder of the proof of this theorem of Price. So the main lemma that connects the black box result of Price on the previous slide to Price's theorem is the following lemma. So let's suppose that we have two D cones, F and M, one contained in the other, with compact bases. And suppose we have a Radon measure mu and a point A in its support so that the following holds. So first of all, the set of tangent measures of mu at A are all contained inside M. Secondly, the set of tangent measures contains at least one of the tangent measures from F. And finally, if we look at the blowups of mu in balls center at A of radius r, as r goes to 0, then, so recall that this blows up the measure from the ball center at A of radius r to a measure inside the unit ball. So the distance between these measures in the unit ball and the cone F, the lim supremum of these is at least epsilon naught. So in other words, as we blow up the measure mu, there exists some sequence of radii going to 0, so that when we blow up the measure mu at ball center A of with radii equal to the sequence, that the distance to the cone is big. So if these conditions are satisfied, then for epsilon small enough, we can find some measure nu, a tangent measure of mu at A, that's not inside the set F, but its distance to F is exactly equal to epsilon, inside the unit ball, and the distance between nu inside any ball center at 0 of radius r bigger than 1 to the cone f is at most epsilon. Okay, so in practice, what's going to happen is that the d cone m is going to be the class of uniform measures, and the cone f is going to be the set of flat measures. So that's how we'll apply it later. So I won't go through the whole details of the proof. I'll just kind of sketch the ideas. Basically, it's an application of the intermediate value theorem. Okay, so notice that condition 2 says that instead of tangent measure, mu has a tangent measure in the cone f. So this implies that we can pick some constant ci and some radii ri going to 0, such that if we look at ci ta ri mu, this converges weakly to some measure, let's call it nu prime, let's say, that's in curly f. Okay, so what this means then is that if we look at d1 of ta ri mu to f, now recall that this distance function is invariant under scalar multiples of the measure in the left coordinate. So this is equal to d1 ci ta ri mu to f. And because this is continuous, d1 is continuous with respect to weak convergence, this converges to d1 of nu prime curly f. But since nu prime is an element of f, this is equal to 0. Okay, so that means that if we look at the graph of d1 tar mu, so the distance between in the unit ball between tar mu and the cone f, here's what's happening. So we can find a sequence of radii, so r1, r2, r3, r4, etc., going to 0, so that the distance is dipping down and getting smaller and smaller and converging to 0. Now, if we look at condition 3, what does this tell us? This tells us that the limit supremum of this distance here is at least some epsilon 0. So that means that for infinitely many radii going to 0, the distance function is getting close to epsilon naught, or is large infinitely many times, which means that we can pick a sequence of radii, so let's say S1 and S2, S3, so on and so forth, where with respect to these radii, the d1 of ta, so if we put like si here, then this distance would be at least epsilon 0 over 2, let's say. Okay, so now the idea is that we've picked these radii so that each s comes between two r's, okay? So now to find this measure nu that we want, we use the intermediate value theorem. So notice that if we look at this graph, between S1 and R1, there must exist some number ρ1 where the graph hits the epsilon line. So that is to say, when this distance function is exactly equal to epsilon. And then if we look between S2 and R2 over here, we can find another point, ρ2, where the distance is again equal to epsilon, and so on and so forth. We can find so I'll draw ρ3 there, and so on and so forth. So we can find some sequence ρi going to 0, so that if we look at the distance between ta ρi mu and f, that this is equal to epsilon exactly. Okay. Now, because mu has compact basis, or because m has compact basis, and the set of tangent measures is contained in this cone with compact basis, then that implies that we can pick a sequence of constants. So let's say some constants di, so that when we take them times ta ri mu, that this measure here converges weakly to some measure, let's call it nu. Okay, so let me write down a different color. So this measure is converging weakly to some measure nu. Okay, so thus this will converge to nu f. And so now we found a tangent measure nu whose distance to the cone f is exactly equal to epsilon. Okay, so that proves the first part of this lemma. The thing that we haven't verified is that if we look at radii r bigger than 1, that the distance between nu and the cone f is at most epsilon. But the details there are not too bad to verify, so we'll just leave it for you to read that in the notes. So now we show how to use the previous lemma and the black box result of price to prove Price's theorem. So let's suppose we have a Radon measure mu such that the m-dimensional densities of mu are exist at almost every point. So the corollary from the tangent measure theorem on the first slide says that if this is the case, then at almost every point A, the set of tangent measures must contain at least one flat measure. And recall from last week, we also know that the tangent measures are all uniform. Now, for such a point A, suppose that we can find a tangent measure lambda that is not in the space of flat measures. And let's suppose that lambda has the following form. It's the limit of ci ta ri mu for some sequence of radii r sub I converging to 0. Okay, so notice that if we take the limit supremum of the d1 distance of tar mu to the cone G, that's at least the same limit if we just take the limit along the radii r sub I. Then recall that this distance is invariant if we multiply this measure by a constant. So that means that this is equal to the limit of d1 ci tar mu. And then because d1 is continuous in the weak topology, that means that this is equal to d1 of the limit of the sequence, which is lambda, the distance between lambda and g, which because lambda is not an element of G, and because G has closed basis, this distance is positive. So we'll let epsilon naught be this positive distance. Okay, so now the previous lemma implies that there exists some tangent measure of mu at A, whose distance inside the unit ball to the cone G is exactly equal to some positive number epsilon. And so that for any ball center at 0 of radius r bigger than 1, the distance to the cone is at most epsilon. Now, by the black box result of price, this implies that nu must actually be a flat measure. And so we get a contradiction because, well, here we had concluded that nu had positive distance epsilon away from the cone. But if nu is an element of the cone, that means that the distance has to be 0. And so that's how we get our contradiction, which means that no such measure lambda can exist, which means that this here is the empty set. And in fact, all tangent measures of mu at A are flat at almost every point A.